Hey students, today's lesson is on comparing populations. So we'll start with some vocabulary. And we're going to be talking about symmetric distributions compared to skewed distributions. So a symmetric distribution is one in which the data points are evenly distributed. On a skewed distribution, the data points are concentrated to one side or the other. So here we see an example of a symmetric distribution where the left side, if we look at where the middle is, the left and the right side look pretty similar to each other. So that's a symmetric distribution. And then on the left-hand side, we have a skewed left distribution, and here we have a skewed right distribution. So on either of these, if we look at where the center is, we can see that most of the data points are to one side or the other. So we have like a lot of data points concentrated to the left over here, and we're going to name it skewed right because the tail goes to the right. In this one, we have a lot of data points kind of concentrated to the right, and we call it skewed left because there's some data points to the left that are skewing it this direction. All right, so let's look at some populations here. Here we have a double dot plot showing the time that each candidate in a debate spent answering each of 15 questions. So we can kind of compare the data to see, it looks like candidate A generally spent more time on the questions than candidate B, but that's not what we're being asked. We're being asked if each distribution is symmetric or skewed. So let's look at just candidate A, and it looks like if here's the center, the left and the right are pretty similar in shape. I wouldn't say it's skewed one direction or the other. That's pretty symmetric. And then if we look at candidate B, we kind of have this center right here, and the left and the right side are pretty similar to each other. So that is also symmetric. So both of these are symmetric. They're not the same data points, but both sets of data are symmetric. Okay, now here's some more vocabulary. Measures of center are measures that describe a typical value of a data set. So examples, mean, median, and mode. You've done these before. So mean is the sum of the data divided by the number of data values. This is a good measure of center to use if the distribution is symmetric. The mean is a great way to measure the center. The median is the middle number, or the mean of two middle numbers if it's an even number of data points. And this is a good measure of center to use when the distribution is skewed. So in other words, if you have some data points that are kind of way out in one direction or the other, if you just pick the middle data value, that all of those outliers are less likely to impact your measure of center. So the median would be a better measure of center in that kind of a situation. Okay, so let's go ahead. Because we saw that each of these distributions were symmetric, mean is a good measure of center for us to use. So let's find the mean for each of these. So for candidate A, we're going to add up all of the times and seconds that candidate A used, and then we're going to divide by 15 because we have 15 data points. So we're going to add 50 plus 60 plus 60 plus 70 plus 70 plus 80, 80, 80, 90, 90, 90, 100, 110, 110, 120. Add all of those up, we get 1,260. Divide by 15 and we get 84 seconds. Now, it's always a good idea to look at your mean and make sure measure of center means it should be somewhere in the center of your data. So here's 84 about right here. That seems okay. If we ended up with a value way over here, we'd say, oh, that doesn't seem like it's in the center. Okay? Now let's do candidate B. So this time we're going to add up 30 plus 30 plus 30 plus 40 plus 50 plus 50, 60, 60, 60, 60, 70, 70, 80, 90, and 90. Divide all of that by 15. Okay, so when I added all of those up, I got 870 divided by 15 is about 58 seconds. Okay, so again, let's check and make sure that's kind of in the middle. Here's 58 seconds. Yeah, that seems pretty reasonable in this case. So that's the mean of both of those. Okay, now we're going to move on to another kind of measure, and that's a measure of variation. So a measure of variation describes the distribution of the data set. So how spread out is the data? So rather than saying this is a typical value, like a measure of center, a measure of variation just says how spread out is the data. So range, mean absolute deviation, and interquartile range are examples here. You may or may not have heard of these before. Mean absolute deviation is the average of how much each data point differs from the mean. This is a good measure of variation when the data is symmetric. So with a symmetric sample of data, the mean is a good measure of center, the mean absolute deviation is a good measure of variation. If the data is skewed, interquartile range is a better measure of variation. And that's the range of the middle half of the data. So just like the median helped make it so that all of those outliers didn't really have an impact, the same is true for an interquartile range, because you're only worrying about the middle half of the data, not anything that's on the edges. Okay, so let's look at some examples. Okay, so here we have this same data that we were using for the mean, and we're going to find the mean absolute deviation. So for candidate A, we found that the mean was 60. So we need to figure out how far is each data point from the mean. Okay, so if this is 60, right? Sorry, it wasn't 60, it was 84. Let me fix that. The mean was 84. Okay, so 84 was right about in here. So we need to figure out how far each data point is from the mean. So if on this question the candidate used 50 seconds, 84 minus 50 is 34. So we're going to use this data point, we're going to count as 34 because it's 34 seconds from the mean. These two data points are at 60 seconds, so 84 minus 60 is 24. 84 minus 70 is 14. 84 minus 80 is 4. 90 minus 84 is 6. 100 minus 84 is 16. 110 minus 84 is 26. And 120 minus 84 is 36. Now we're just going to add these up and divide by our 15 data points. So our MAD, our mean absolute deviation, will be 34 plus 24 plus 24 plus 14 plus 14 plus 4, 4, 4, 6, 6, 6, 16, 26, 26, 36. Add up all of those data points and divide by the 15. So that was 244 divided by 15, which is 16.3. So our average question was about 16.3 seconds away from 84. It gives you an idea of how spread out the data points are. If the number was smaller, our data would be more squished together. If the number was bigger than that, they would be more spread out. Okay, let's take a look at candidate B. Candidate B, the mean was, I better look this up this time. The mean for candidate B was 58. Okay, so here we're looking at 30 seconds. 58 minus 30 is 28. 58 minus 40 is 18. 58 minus 50 is 8. 60 minus 58 is 2. 70 minus 58 is 12. Kind of seeing the pattern here, 22, 32. Okay, now we're going to add all of these up and divide by 15 because we have 15 data points. So 28 plus 28 plus 28 plus 18 plus 8, 8, 2, 2, 2, 2, 12, 12, 22, 32, 32. Add all of those up and we have 236 divided by 15, which is about 15.7. So it looks like candidate B had a little bit of a smaller mean absolute deviation. The data is a little bit more concentrated, but not a whole lot more. Okay. So let's practice finding the mean and the mean absolute data set, the mean absolute deviation for a small data set here. Here we have 6 values, so we're going to find the mean first. We're going to add up 2 plus 5 plus 10 plus 12 plus 14 plus 15 and divide that sum by 6 because there are 6 data points. So we add up, that's 58 divided by 6, which is about 9.7. Kind of look to see that that's somewhere in the middle. That seems reasonable, 9.7. Now, the mean absolute deviation, we need to figure out how far each of these data points is from 9.7. Okay, so I'm going to list the 6 numbers over here. So 9.7 minus 2 is 7.7. 9.7 minus 5 is 4.7. 10 minus 9.7 is 0.3. 12 minus 9.7 is 2.3. 14 minus 9.7 is 4.3. And 15 minus 9.7 is 5.3. So we're going to add these all up. 7.7 plus 4.7 plus 0.3 plus 2.3 plus 4.3 plus 5.3. And we get 24.6. We divide by our 6 data points, and we get the mean absolute deviation is 4.1. All right, let's move on here. This is a review. Hopefully you've seen a box and whiskers plot before, but if you haven't, a box and whisker plot is a way to divide a set of data into 4 equal parts or quartiles. So what we call it a box and whisker plot because you can see a box and 2 whiskers. This first whisker is the first quartile of data. So all of the data values in the first quartile would be between this point and this point. The box contains the middle 50% of the data. Here's the second quarter of data. Here's the third quarter of data. And then the last quarter is in this last whisker. So that's the 4th quartile or the highest 1/4 of the data points. So if we want to kind of look at some different populations here, if we want to compare the cost of speeding tickets in 2 different states, let's look at the box and whisker plots that show a random sample of speeding tickets issued in the state. So first of all, are the distributions symmetric or skewed? So let's look at state A. If here's the median value, half of the data values are concentrated in this little tiny piece, and the other half of the data values are spread way out. So that is a really skewed sample of data. State B is a little bit closer to being symmetric. We can see that the 2 sides are closer, but if we look and see the bottom half of the data is spread between 30 miles per hour, and the second half, or the higher half, is spread out 60, or not miles per hour, dollars, sorry, cost. So this is spread out among $30, and this is spread out among $60. So both of these are skewed data samples. So if the data is skewed, we know that median is a better measure of center than mean, and interquartile range is a better measure of center than mean absolute deviation. So we're going to find both of those. Let's go ahead and do the median first. So the median of A is going to be right here, right in the middle. So that's $70. And the median of B is right in the middle where they show the line on the box, and that's $80. So which state tends to have more expensive tickets? I would say state B tends to have more expensive tickets. Which state has more variance, though? So let's go ahead and find the IQR, the interquartile range of A. And that's going to be the range of the middle part of the data. So the range between the 3rd quartile and the 1st quartile. So that's 80 minus 60. That is an interquartile range of 20. and the interquartile range of B will be from 100 to 70. So that's 30. So if we want to know which state has more variance, B has more variance, right? It's a little bit more spread out. Okay, let's find the median and the interquartile range of this small set of data. The first step when you're finding the median or the interquartile range is to put the numbers in order from smallest to largest. And it looks like this one is already written in order from smallest to largest. So the median is right, the middle set of data or the average of the middle two. So our median is going to be right here between 10 and 12 at 11. That's our median. Then for our interquartile range, we need to find the middle of the upper half of data and the middle of the lower half of data. So as we're looking at the upper half, we only have 3 values. Here's the middle is 14. And in the bottom half, the middle or median of this set of data is 5. So the interquartile range will be 14 minus 5 or 9. And that's the interquartile range. All right, that is it. Go ahead and try a few on your own. I'll see you soon.